This is Kuntal Chakraborty, Assistant Professor of Electrical Engineering Department, Greater Kolkata College of Engineering and Management, GIS Group. I'm just going to give a lecture on an important topic, that is pin diagram description of 8085 microprocessor. This is the IC of 8085 microprocessor. It has 40 numbers of pins, where we have some address bus, data bus, and power signals, frequency signals, and externally initiated signals, means interrupt signals. All these things we have, and all these pins that can be classified into some category, and these signals can be categorically divided into 6 groups. One is the address bus, second one is the data bus, third one is the control and status signals, and interrupts and externally initiated signals, serial input output ports, and power supply and frequency signals. Now, if the pins are classified into six different categories, and that signals can be categorically drawn into a picture, here we are seeing that address bus, that is basically divided into 2 parts, higher order address and multiplex lower order address data bus. And externally initiated signals we have, external signal acknowledgement we have, and serial input output ports. All these classified signals are drawn here, and now I will try to explain all the signals. First is the address bus. In 8085 microprocessor has 16 address lines, and these 16 bit of address bus that can be divided into 2 parts. One is a higher order address, that is A8 to A15, and another one is a lower order multiplex address data bus, that is AD0 to AD7. And this is a unidirectional bus, means the address can be done into a single way, because if the microprocessor want to address any input output device or memory devices, then it will send the address to the peripheral device or memory device for the addressing. So that's why it is unidirectional. And next is a data bus, which is a 8-bit of data bus in 8085 microprocessor have, and it is basically multiplexed with the lower order address, that is D0 to D7, and this one is a bidirectional. By using this data bus, we can send data to the peripheral device or memory device, as well as we can microprocessor can accept data from a peripheral device or memory chip, from a memory chip. So this is the address and data bus by which the addressing can be made, and the data that can be transmitted to the peripheral device or memory device, and that can be received data from a peripheral device or a memory device. Next, multiplex lower order address data bus, which is very important. Here the AD0 and AD7 serve a dual purpose role, means it can be used as address bus as well as data bus, lower order address bus as well as data bus. Now how it can be done? Here with this lower order address bus, a latch LS373 is connected, and a signal called ALE, that is the address latch enable signal, that will send to the latch to activate the address. For execution of any instruction during the earlier part of the cycle, these lines are used as an address bus. Means in the earlier section, the ALE that will be active high, and that multiplex address data bus behave like a address bus, and after the addressing the ALE, now that will be low, and that multiplex address data bus that will behave like a database, means during the later part of the cycle it is used as a data bus. Now control and status signals. We have some control signals, read and write. Suppose I want to microprocessor want to read some data from a memory or input device that is connected with a microprocessor, then it will send a read bar signal to the peripheral device or memory device to read the data from a memory or peripheral device. At the same time, if microprocessor want to write some data into a memory or into a outer device, if it wants to send some data into a outer device, then a write signal that will be sent to it, and finally the microprocessor can send the data into a outer device or input output device, as well as it can write the data into a memory. And we have some status signals, S0, S1, IO/Ember. Basically these signals basically give us different status, microprocessor of different operations status that can be seen by using these three lines. And S0 and S1 IO/Ember basically give us different status, whether it is operated as whether it is fetching any opcode, whether any input output operations is going on or not, then status that can be seen by using this status line S0, S1 and IO/Ember. And I already discussed the functions of ALE. ALE is actually a control signal that will basically send to the latch that is connected with the multiplex lower order address data bus. By using ALE, we can segregate lower order address and data. When ALE is high, then the multiplex address data bus that will behave like a address bus, and when it is low, then it will behave like a data bus. Now these are the read, write and ALE are the control signals, and these are the very important one because these group of signals basically control different operations of microprocessor. Next, IO signal I already described. Basically this is a input when any input output operation is going on by the microprocessor. At this time, this pin that will generate a 1 signal means a active high signal, and when a microprocessor is operating any memory related operation, at that time it will send the pin that will send a 0 signal. It will generate a active low signal. And we have S0 and S1. This will give us different operations. I already discussed whether it is a read operation or write operation, input output read, input output write, or fetch operations. So now this is the table where we can see different operation status that can be seen by using this table. Now if IO/Ember is 0 and S1 is equal 1 and S0 is equal 1, then this is basically opcode fetch operations, and this is basically a read operations. That's why the read signal that will be 0. Similarly, memory read IO/Ember, this is a memory related operation. That's why that will be 0, and the status signal will be 1, 0. And obviously this is a memory related operation. Memory read is happening. That's why read signal that will be active. Memory write signal. Memory write operations where the IO/Ember that will be equal to 0 because this is a memory related operation, as well as S1, S0 that will be equal to 0, 1, and as it is write operation, then the write signal that will be sent and means the write signal that will be active at that time. And IO read, that IO/Ember that will be equal to 1 and S1, S0 that will be equal to 1, 0. This one is 1 because this is an input output operation. That's why IO/Ember that will be equal to 1. At the same time, a read signal that will be generated because the read operation is going on through the IO devices. At the same time, IO write operations, IO slash M bar, that will be equal to 1 because this is a input output related operations, and S0 S1 that will be equal to 0 1, and the write signal we are getting as 0, means now this is active, means the write operation is going on. So these basically give us some status whether the opcode phase is going on, memory read, memory write, input output read, input output write is going on or not. So this is the interrupt acknowledgement status. 1 1 1 means all are 1, means the interrupt acknowledgement done, means INTA bar is equal to 0, means any interrupt occurred after the interruption the microprocessor will send interrupt acknowledgement signal to the peripheral device by telling that microprocessor accepted the interrupt request. So this status is actually give us the acknowledgement of interrupt. Halt, that is Z00, and hold H, Z don't care, reset Z don't care. So these are the status by which we can understand what kind of operation is microprocessor doing. Next is a control and status signal. This is already I discussed ALE. ALE is a control and status signal. I already discussed ALE, basically used for the segregation of address and data bus. So I already discussed ALE. Now we have interrupts and externally initiated signals. In 8085 microprocessor can be interrupted by 5 lines, that is trap, RST 7.5, RST 6 point and RST 5.5. Basically, whenever microprocessor is performing a program, at that time a peripheral device may request to perform any task by using 8085 microprocessor. So at this time microprocessor may send an acknowledgement to the peripheral device by telling that he accepted the data. Means when acknowledgement happening, means urgent work is actually try to perform by the peripheral device, and the access of this microprocessor that can be done by using the microprocessor by pausing the current operations, and acknowledgement done through INTA signal. So next is the reset in signal, that is the externally initiated signal. If you send a reset in signal to the microprocessor, this is an active low signal. If active low signal sent to the microprocessor, then the microprocessor that will be reset. At the same time, if active high signal that will be sent by the reset out pin to the peripheral device, then the peripheral device can be reset. Means this signal is used to reset all the connected device when the microprocessor is reset. And a ready signal, which is very important. Suppose CPU has a higher frequency and a peripheral device connected with the microprocessor, its frequency is low. Now whenever microprocessor is trying to send some data to the peripheral device, because due to the speed of the peripheral device is very low, so it cannot accept the data as fast as sending the microprocessor. So that's why data may be corrupted. So that's why the ready signal, basically this is a in signal, externally in, it will send to the microprocessor by telling that this peripheral device is ready to accept the data. Then only microprocessor can send the data to the peripheral device. So this is the operation of ready signal. Next, hold and HLDA signals. These are also the externally initiated signals. Basically, hold signal, which is basically used for the DMA operations. If some peripheral device want to access the address or data bus of microprocessor, 8085 microprocessor, then it will send a hold signal to the microprocessor by telling that the peripheral device wants to use the address and data bus of microprocessor. If the microprocessor is performing any task, then microprocessor will complete that task. After that, the hold request that will be accepted by the microprocessor, and finally it will send a microprocessor will send a HLDA, that is a hold acknowledgement signal, to the peripheral device by telling that microprocessor accepted the hold request. So this is the operation of HOLD and HLDA. So these are the externally initiated signals. Next, serial input-output ports. The data may be transmitted parallelly as well as serially. But if microprocessor want to send some data serially, then we need SOD and SID line. By SOD, we can say these two lines basically used for the transmission of serial data in input and output side, and for the case of SOD, basically the SOD is set and reset as specified by the SIM instructions. Similarly, the data on this line for the SID is located into accumulator whenever a RIM instruction is executed. So SOD and SID, for SOD the SIM instruction is used for the execution, and for SID the RIM instruction is used for the execution. So these two signals are very important for the serial communication. Next, VCC, that is microprocessor is operated with a plus 5 volt supply, and we have ground, that is VSS, and microprocessor is operated with a 3 megahertz of frequency. That's why we have to provide a 6 megahertz crystal oscillator within the 2 pin X1 and X2, a crystal oscillator that is connected in between X1 and X2 to provide 3 megahertz of frequency to it. Now we have a clock out. This signal can be used as a system clock for other devices. Basically, the clock frequency that we are getting from the microprocessor, that can be used for other peripheral devices. Thank you.